Hello, my dear students. I continue with you my online lecture. I stay at home and I teach you from home and continue my quarantine days, of course, at home. Okay, my name is Kamala Badalova. I am an assistant professor of the General and Toxicological Chemistry Department. And today the topic of our lecture will be the general characteristic of D elements, the elements of third B subgroup, third and fifth B subgroups. Okay, about the characteristics of the D block elements, which characteristics they have. At first, let's define what is D block elements. These elements which have the partially filled D orbitals as a ground state or in one or more of their ions. This is our particle table, and you can see our D orbitals. And D block elements, the elements of periodic table belonging to group 3 to 12 are known as D block elements because in these elements last electron enters in D subshell or D orbital. The D block elements lie in between S and P block elements in the long form of periodic table. And in this table you can see all D block elements, the group of scandium, titanium, vanadium, chromium, manganese, the group of the iron, cobalt, nickel, copper and zinc. First series, second series, third series and fourth series. And in this row you can see the distribution of the electrons in last level, energy level. Transition elements is defined as the one which has incompletely filled D orbitals in its ground state or in any one of its oxidation states. For example, a transition element should have partially filled n-1 D orbital. But about the electronic configuration, as you remember, during our lectures, I told you that how can we differ the elements of A subgroups and B subgroups. But A subgroup elements, they have same number electrons in last level in which group they are stay. But the B subgroup elements in last level, they have just 2 electrons in last level, but except chromium and the copper. Why? Because they have abnormal electronic configuration. But how D block elements and transition elements can we differ these elements? All D block elements aren't transition elements, but all transition elements are D block elements. All D block elements aren't transition elements because why? Because D block elements, like zinc, have full D10 configuration in their ground state as well as in their common oxidation state, which isn't according to definition of transition elements. About general properties of D block elements, about atomic and ionic size, ionization, enthalpy, oxidation states, colored ions and the catalytic properties. Melting and boiling points are high, a large, and from this graph you can see a large number of unpaired electrons take part in bonding so they have very strong metallic bonds, and hence they have high melting point and boiling point. In this slide you can see about the atomic radius, but this slide related to the atomic radius of fourth period transition elements: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Along the rows, nuclear charge increases, but the penultimate d subshell has a shielding effect, so atomic and ionic size remain almost same. The radius of the third 5d series are virtually the same as those of the corresponding members of the second series, as like this series of the elements. This phenomenon is associated with the intervention of the 4f orbital. The filling of 4f before 5d orbital results in a regular decrease in atomic radius called lantanoid contraction, which essentially compensates for the expected increase in atomic size with increasing atomic number. The net result of the lantanoid contraction is that the second and the third d series exhibit similar radius. For example, zirconium and hafnium. About ionization enthalpy, in this slide we can see that the chromium has ionization enthalpy more ionization enthalpy or ionization energy, they are same. Chromium has more than manganese and more than vanadium. And for the copper has more ionization enthalpy more than zinc and more than nickel. For the third ionization energy, manganese has more ionization enthalpy than iron. Due to an increase in nuclear charge which accompanies the filling of the inner d orbitals, there is an increase in ionization enthalpy along each series of the transition elements from left to right. However, many small variations occur. About oxidation states, transition elements have variable oxidation states due to very small energy difference between n-1d and ns subshell electrons from both the subshell take part in bonding, and in this graph you can see the oxidation degrees of some elements. The most common ones are in bold types. For example, for scandium +3, for zinc +2. For example, for chromium we have +2, +3, +4, +5 and +6, and you can see for another elements. The elements which give the greatest number of oxidation states occur in or near the middle of the series. For example, manganese exhibits all the oxidation states from +2 to +7. Low oxidation states are found when a complex compound has ligands capable of p by acceptor character in addition to sigma bonding. For example, in our compound, the oxidation degree, the oxidation state of nickel and iron is 0. Why? As you remember from the general chemistry, from the coordination compounds, what is this? This is carbonyl. They are like neutral ligands. They have the oxidation degree 0 because nickel and iron has the oxidation state is 0. About the colored ions, most of the transition metal compounds, ionic as well as covalent, are colored both in solid state and in aqueous state. In generally, the elements ions having unpaired electrons produce colored compound. And from our slide, you can see some compounds. For example, about titanium oxide, scandium oxide, and zinc sulfate, heptahydrate. They are colorless, but sodium chromate has yellow color. Potassium ferricyanide, green-yellow fluorescence. Nickel nitrate has green color. Vanadium sulfate dihydrate, it has blue color. Manganese chloride tetrahydrate, pink color. Cobalt chloride, the color of the cobalt chloride can change. It depends on the humidity from sky blue to purple to pink color. And at last, copper sulfide has blue color too. And in this picture, we can see D transition to the complex in electronic excited state and complex in electronic ground state. About the catalytic properties, vanadium oxide in contact process, vanadium 5 oxide in contact process, finally divided iron in Haber's process, nickel in catalytic hydrogenation, cobalt synthesis of gasoline. This property is due to presence of unpaired electrons in their incomplete of d orbitals. Variable oxidation state of transition metals in most cases provide a large surface area with free valency. But now we go to the description of each group, because we have today 3 B, 4B and 5th B subgroups. At first, we will describe group 3B. In third B group, we have scandium, yttrium, lanthanum, and actinium elements. They are metals. Okay, for first, scandium. Scandium derived from Latin Scandia, which means Scandinavia. Scandium was discovered by Lars Nilsson in 1879 in Sweden. Scandium is found in minerals extending tall whittle and gaudelin at Scandinavia and Madagascar. About the properties, scandium is a silver-white metal that changes color to yellow if it reacts with air. Physical properties: density, about melting point, boiling point, form 25 degree, and color white silver. About atomic properties, what is atomic properties and which properties we can describe here? Atomic number 21, the mass number 44, this atomic mass 45, electron configuration 3d14s2, atomic volume and electron affinity, electronegativities, ionization energy, first ionization energy, second ionization energy, and third ionization energy. Main oxidation state +3, other oxidation states +1, +2, shape crystal, hexagonal unit cell. In the solid state of scandium has the hexagonal crystal structure, but these properties related to the atomic properties of the scandium. Now about chemical properties and the chemical reactions. Chemical reaction with water. When heated, the scandium will dissolve in water to form a solution consisting of ions scandium 3 and hydrogen gas. Reaction with oxygen. In the reaction with the air or combustion, quickly it will form scandium 3 oxide in solid state. Reaction with halogens. Scandium is very reactive when it reacts with all the halogens to form 3 halide elements. 3 halide elements. Example with fluorine, with chlorine, bromine, and iodine. The reaction with acid. Scandium readily soluble in hydrochloric acid to form a solution containing ions scandium 3 and hydrogen gas. Example, this our ion of the chlorine anion, hydrogen, and the scandium ion. But where can we use scandium? Chloride scandium, where these compounds can be found in halide lamps, fiber optic, and laser ceramic electrolyte. Primary application of the element scandium alloy is as aluminium. Scandium is used for sports equipment wax and have a high quality. Other applications is the use of scandium iodide for light that provide a high intensity. Scandium oxide 3 oxide is used as a catalyst in the manufacture of acetone. For health and environment effect, scandium is not toxic but need to be careful because some scandium compounds may be carcinogenic in humans, but it can cause liver damage if it accumulates in the body. Together with aquatic animals, scandium can cause damage to the cell membrane, thus providing a negative effect on the reproductive and nervous systems. Scandium can contaminate the environment, especially from the petroleum industry and from the disposal of household furniture. Scandium continuously accumulate in the soil. It will trigger the concentration in the human body and animals. About second element, yttrium. Yttrium, as you know, is a element of the third B subgroup, listing in the period 5. Yttrium included in the transition metal. Yttrium was discovered by researchers from Finland named John Godlin and isolated in 1794 by Friedrich Wöhler in 1828 in the form of impure extract of yttrium from yttrium chloride anhydrous reduction with potassium. About properties, physical properties: density 4.5 gram per centimeter, melting point, boiling point in Celsius, in Fahrenheit, and in Kelvin, form 25 degrees, this is solid, color silver. About atomic properties: atomic number of the yttrium 39, mass number 88.99 is like 89, close 89, electron configuration 4d1 5s2, atomic volume, affinity electron. They are atomic properties. About chemical properties of the yttrium: reaction with water. When heated, each yttrium metal will dissolve in water to form a solution consisting of ion yttrium 3 and hydrogen gas. Reaction with oxygen. In the reaction with air or combustion quickly, it will form yttrium 3 oxide. Reaction with halogens. Yttrium is very reactive when it reacts with all the halogens to form 3 halide elements. Reaction with acid. Yttrium easily soluble in hydrochloric acid to form a solution containing ions of yttrium 3 and hydrogen gas. Where can we use yttrium? Later we will speak a little about the application of yttrium. Aluminium, yttrium, garnet, yttrium 3, aluminium 15, oxygen 12 is used for laser, stimulant and diamond. Yttrium is also used to increase the strength of the metals aluminium and magnesium alloy. For health, yttrium danger if react with the air is if inhaled by humans can cause cancer, and if it accumulates in excess amounts in the body, causing damage to the liver. Yttrium can contaminate the environment, especially from the petroleum industry and from the disposal of household furniture. About the lanthanum, this is third element of this group. Lanthanum discovered in Sweden by Carl Gustav Mosander, which is a great chemist with the nickname Father Moses in 1893. Lanthanum derived from Latin lantana, which means heater. About physical properties: lanthanum is a silvery white metal. Lanthanum is a silvery white metal, malleable, strong but soft enough to cut with a knife. Lanthanum is one of the highly reactive metals. Lanthanum oxidizing rapidly when exposed to air. Lanthanum has a density of 6.18 gram to centimeter cube. Melting point 1193.2 Kelvin. Boiling point of 3693 Kelvin. Chemical properties, it can react with water. Lanthanum is quite electropositive and reacts slowly with cold water, but fairly quickly if it reacts with hot water to form hydrogen gas and hydroxide lanthanum and hydrogen gas. Reaction with oxygen. In the reaction with the air or the combustion air, quickly it will form lanthanum 3 oxide. With halogens, also as in case of scandium and yttrium, lanthanum metal reacts with all halogen elements, form lanthanum 3 halide. Where can we can we use lanthanum? For what? Lanthanum oxide is used to create a special optical glass that serves infrared camera and telescope lenses. If lanthanum is added in the steel, will increase the softness and durability of the steel. Lanthanum was used as the main material in the carbon arc electrodes. Lanthanum salts contained in the solid catalyst used in the petroleum refining process. One of the uses of the compound lanthanide goal is the film industry for studio lighting and the projection. For health, lanthanum is very dangerous if the fog and the smoke inhaled with the influx of oxygen, and in the long term will be able to cause embolism if the person can breathe lanthanum affected by lung cancer. If accumulates in the body, the lanthanum threatening liver organ. Lanthanum also can contaminate the environment, especially from the petroleum industry. Actinium. The word actinium comes from the Greek activism, actinos, which means light. Actinium was discovered in 1899 by André Louis Daillon, a French chemist who separates from the mixture actinium. Actinium is separated from uranium ores. About the physical properties, you can see in our slide density, melting point, boiling point, about the state, solid state, about color, white, silver, melting, heat, about heat of the operation, material capacity. Chemical properties. Actinium shows chemical properties similar to lanthanum. Reaction with oxygen. Actinium is flammable from actinium 3 oxide. Useful. The properties of the radioactivity of actinium 150 times larger than radium, making it possible to use actinium as a neutron source. Actinium-225 is used as a Helling agent. This is isotope of actinium. Helling agent for the radioimmunotherapy. Actinium-227, as this isotope, is highly radioactive and adverse health effects. The greatest danger from radioactive transform life, and we know it is a danger to reproductive system and the nature of the decline, even with a low dose carcinogenic, which cause a decrease the immune system. But now we go to the fourth B, subgroup. But this subgroup form a subgroup of titanium, zirconium, hafnium, and rutherfordium. About the electronic structure of each element for titanium, zirconium, hafnium, and the rutherfordium. You can see from our slide the atoms of the, and you can see that each element in the last level they have 2 electrons in s orbital. The atoms of the elements of the titanium subgroup have 2 electrons in the outer layer and 2 electrons in outer layer and 10 electrons in the second layer from the outside. 2, for example, for the titanium, 2 of which are on the d sub level. Example here, 2 electrons in the d orbital. About titanium, the chemical element, you can see here the symbol of the titanium with serial number 22, atomic weight 47.88. Solid silver metal. Titanium is a chemically active element. In compounds it has oxidation states +4, less often +3 and +2. At ordinary temperatures and up to 500 and 550 degrees Celsius, it is corrosion resistant, which is explained by the presence of a thin but strong oxide film on its surface. Zirconium element with atomic number 14. Zirconium is characterized by an oxidation state of +4. The lower oxidation states +2 and +3 are known for zirconium only in its compounds with chlorine, bromine, and iodine. Hafnium chemical element with atomic number 72, atomic mass 178.49. Neutral hafnium consists of 6 isotopes. The most characteristic oxidation state of hafnium is +4, valence 4. Compounds in oxidation states +3 and +2 are unstable. And at last element of this group, rutherfordium. Rutherfordium until 1997 also Kurchatove, chemical element number 104 in the periodic system. Rutherfordium is a highly radioactive, artificially synthesized element. This element can't be used anywhere, and little is known about it, since it has never been obtained in microscopic quantities. Rutherfordium is the first transactinoid element. It is predicted chemical properties are close to hafnium. Okay, being in nature, but in which compound we can find in nature these elements? About titanium, in free form doesn't occur. The most important titanium minerals are rutil, ilmenite, titanomagnetite, perovskite, and titanite or the sphene. About zirconium, zircon where 67.1% of zirconium 4 oxide, badalite, and various complex minerals, eudalite, and others are widespread in nature. Hafnium refers to scattered elements. It doesn't form its own minerals. It is found as an impurity to zirconium minerals. But which characteristics has these elements? About titanium, atomic radius of titanium, zirconium and hafnium, we can see these numerals, content in the Earth's crust, and the content in the human body. As you see, but in Earth's crust, titanium 0.56, zirconium 1.9, multiplied 10 in the minus 2 degree, and hafnium 5.3 multiplied 10 in the minus 4 is very little content. But in human body, we have titanium and zirconium, but they are, as you know, these elements, they are micro elements, and a very little quantity of this compound we have in our body. But about hafnium, you can see this grave is empty. It means that hafnium we haven't in our body. About electronegativity of titanium 1.5, zirconium 1.3, and hafnium also 1.3. The main oxidation degrees of titanium and zirconium, they are same, +2, +3, +4, and hafnium has oxidation degrees +3 and +4. About physical properties, by physical properties, the elements of the titanium subgroup are typical metals that look like steel. Pure metals lend themselves well to machining, but even minor impurities of some elements, hydrogen, oxygen, nitrogen, carbon, and other elements, gives them reliability. Their characteristic constants, about the density, melting point, boiling point, and the conductivity of titanium, zirconium, and hafnium in our table. Physical properties. Titanium, zirconium, and hafnium exist in two crystalline modifications: alpha form with the hexagonal lattice and beta form with the cubic volume centered. Getting a preparation of the titanium ore concentrate is subjected to the sulfuric acid or the pyrometallurgical processing. The product of the sulfuric acid treatment is titanium dioxide powder. Pyrometallurgical method centered the ore with the coke and the treated with the chlorine, receiving a pair of titanium tetrachloride. And titanium tetrachloride vapors produced at 850 degrees reduced by magnesia. And at last we can get titanium by this way. And the resulting titanium sponge is remelted and refined. Ilmenite concentrates are reduced in electric arc furnace, followed by the chlorination of the resulting titanium slag. The titanium is refined by the Yadid method or the electrolysis separating titanium from titanium tetrachloride. To obtain titanium ingots, arc electron beam or plasma processing is used. How can we get zirconium? Enriched zirconium ore is centered at 600-700 degrees Celsius with potassium fluorosilicate. This is fluoride method. At next, potassium fluorocirconate together with hafnium fluorocirconate is leached with water subjected to fractional crystallization to remove hafnium impurities. Then, in the melt, zirconium is reduced by electrolysis. In the chloride method, the ore is chlorinated in the presence of coke. The obtained zirconium tetrachloride is prepared by the sublimation method, then reduced with magnesia. But when using the alkaline method, the ore is centered with the sodium hydroxide, soda, or a mixture of calcium carbonate and calcium chloride. Then acid leaching of the this compound is carried out. Pure zirconium is obtained by thermal decomposition of zirconium tetraiodide in pairs. But how can we get hafnium? Received along with zirconium, it is very difficult to separate hafnium from the zirconium. Analog element always associated with it in nature due to the proximity of their chemical behavior, which is explained by the proximity of the ionic radius of hafnium and zirconium. Separation hafnium 4+ and zirconium 4+. Separation is carried out using the ion exchange and solvent extraction. But after separation by extraction and fractional crystallization, complex hexahafnate of the potassium chloride is obtained. The magnesium, calcium, or sodium thermal contact in an atmosphere of argon or the helium. Hafnium is also obtained by reducing of the hafnium dioxide with calcium at 1300, so high temperature. At last, deep cleaning of the hafnium thus obtained is carried out in a chemical reactor at 600 degrees of Celsius. About the chemical properties of the titanium. When heated in air to 1200 Celsius, titanium ignites with the formation of oxide phases of variable composition titanium oxide. So X because this is variable composition. When heated, titanium interacts with halogens, hydrofluoric, concentrated sulfuric acid, as well as hot organic acids, oxalic acid, formic acid, and trichloroacidic acids reacts with the titanium. And you can see from our slides the reactions of our compounds, of our titanium with some compounds, with acids, for example here hydrochloric acid, hydrofluoric acid, sulfuric acid, and the oxalic acid. Titanium dioxide is unfortunate that it exhibits both basic and acidic properties. Although it reacts mainly with concentrated acids, it slowly dissolves in concentrated sulfuric acid, forming the corresponding salts of tetravalent titanium sulfate, where titanium has a valence 4. In concentrated solutions of alkalis or upon alloying with them, titanates are formed salts of titanic acid and phosphoric titanium hydroxide. The same will happen with concentrated solutions of carbonates or the bicarbonates. This is carbonate and bicarbonate of potassium. With hydrogen peroxide gives orthotitanic acid. This is orthotitanic acid. But when heated with ammonia gives titanium nitrate. When fused with oxides, hydroxide and the carbonates, titanides, and double oxides are formed. Double oxides. This is double oxide. Barium oxide with titanium dioxide. Barium oxide with titanium dioxide, and at last also barium oxide with titanium dioxide. But when heated, it is reduced by carbon and active metals to lower oxides. When heated with the chlorine in the presence of reducing agents, carbon, for example, forms titanium tetrachloride. About the chemical properties of zirconium, zirconium above 800 degrees Celsius interacts vigorously with atmospheric oxygen. Zirconium actively absorbs hydrogen even at 300 degrees Celsius, forming a solid solution and hydrates. With nitrogen, zirconium forms zirconium nitrate at 700-800 degrees. Zirconium interacts with carbon at temperature above 900 to form zirconium carbide. Zirconium reacts with fluorine at ordinary temperature and with chlorine, bromine, and the iodine at temperatures above 200 degrees, forming higher halides, where, for example, X, this is halogen, for example, fluorine, chlorine, bromine, or iodine. Zirconium tetrahalides. Zirconium can react with acids. Zirconium can interact with acid if formation of its anionic complexes is possible. So, finally divided zirconium dissolves in hydrofluoric acid. In a mixture of nitric and hydrofluoric acid and in aqua regia. This is what is aqua regia. This is a mix of 4 moles of the nitric acid, and this is a mix of the nitric acid with the hydrochloric acid. But in this case, for zirconium, we wrote 4 moles of nitric acid and 18 moles of the hydrochloric acid. It depends on the balance. Zirconium is resistant to alkali solutions. Zirconium dioxide doesn't react with water, concentrated hydrochloric acid, or nitric acids. Interacts with concentrated hydrofluoric and sulfuric acid with molten alkalis. Zirconium dioxide reacts with the formation of salt, zirconates. This is potassium zirconate. Upon acidification of zirconate solutions, hydrated gel oxide, zirconium hydroxide is released. About chemical properties of hafnium. By its chemical properties, hafnium is similar to zirconium. Under normal conditions, it is resistant to corrosion due to the formation of an oxide film. Hafnium dioxide. When heated, the chemical activity of hafnium increases. At temperature above 700 degrees Celsius, it reacts with the atmospheric oxygen, with nitrogen. Then at 350 degrees, or 400 degrees, metallic hafnium absorbs hydrogen to form hafnium hydrate. Above 400, they treat gifts of hydrogen. Hafnium interacts with acids only if conditions are created for the oxidation and formation of anionic hafnium 4 complexes. Finally, divided hafnium is dissolved in hydrofluoric acid. The following reactions occur in a mixture of nitric and hydrofluoric acids and aqua regia. Hafnium interacts with concentrated sulfuric acid only when boiling hafnium with sulfuric acid. We can prepare these compounds. Hafnium is resistant to alkali solutions. Hafnium dioxide doesn't dissolve in water, concentrated hydrochloric and nitric acids, but interacts with concentrated hydrofluoric and sulfuric acids. Hafnium dioxide reacts with molten alkalis with the formation of hafnate salts. Hafnate, but the name of this compound, sodium hafnate. About application, for example, how we can where we can apply titanium. In the form of alloys, titanium is used in the chemical industry, reactors, pipelines, pumps, light alloys, osteoprothesis. If it is the most important structural material in aircraft, rocket, and ship building. Titanium is a dopant in some steel grades. As compounds, white titanium dioxide is used in paints, for example, titanium white, as well as in the manufacture of paper and the plastic. Organotitanium compounds, the tetrabutoxytitanium. What is organotitanium? Organic compounds are used as a catalyst and hardener in the chemical and paint industry. Inorganic compounds of titanium are used in chemical, electronic glass, fiber industry as an additive. Titanium diboride is an important component of superhard material for the metal processing. Titanium is used to coat tools. Then about the application of zirconium, hafnium-free metallic zirconium and its alloys are used in nuclear energy for the manufacture of nuclear reactor designs. In metallurgy, it is used as a ligature, good deoxidizer and deoxidator, allowing steels with zirconium up to 0.9% increases their mechanical properties and the machinability. It also makes copper alloys more durable and heat resistant. Zirconium is used very widely in phytotechnics. The production of chemical light source, for example, torches, light rockets, light bombs. In the form of the structural material, it is used to manufacture acid-resistant chemical reactors, valves, and pumps. Zirconium is used to create bone, joint and dental prostheses, and as well as a surgical instrument. And hafnium, where we can apply hafnium. The bulk of the hafnium produced in the form of hafnium dioxide is used for the manufacture of control rods of nuclear reactors and protective shells. It is used as a material for cathode tubes and electrodes in reactors and high pressure discharge tubes. Heat-resistant alloys of hafnium with tantalum, molybdenum, and tungsten are used for the manufacture of combustion chambers of jet engines. And at last, our fifth group, the first element, this is vanadium, because another element we can say as vanadium group elements. Vanadium, that now we'll speak about the vanadium. The symbol for the vanadium is vanadium V. The atomic number is 23. The atomic mass is 50.9, close 51. Vanadium was discovered by Andres del Rio in 1801, by Henry Roscoe in 1867, by reducing vanadium chloride with the hydrogen. Vanadium was named after Vanadis, the mythical Scandinavian goddess of beauty and love. Vanadium was originally discovered by Andres Manuel del Rio, a Spanish-born Mexican mineralogist, in 1801 year. Del Rio extracted the element from a sample of Mexican brown rich ore, later named vanadinite, and he found that its salts exhibit a wide variety of colors, and as a result he named and made the symbol V. Vanadium, the incorporation of vanadium into steels accounts for about 90% of USA. It is a soft silvery gray electron transition metal in its natural form. Vanadium can be found in by-products of mining. It is also a trace element in many different types of rocks. There is also a small amount of vanadium found in human body. It can also be found in aluminium ore and deposits rich in carbon. About the vanadium is again the soft blue silver metal at room temperature. It is atomic number is 23. We told about it. Vanadium has a melting point of 191 degrees Celsius and boiling point 3407 degree molten. Molten vanadium glows with golden. Like all transition metals, vanadium electron shell can bond with other elements. And my dear students, thank you for your attention, and stay safe. Of course, stay at home for your health, good health. Okay, goodbye, and I think that I will see you soon.